Hi, this is Alex from devstories.eu. MicroPython, Episode 7 of 7. Writing a hardware interrupt service routine in a high-level, garbage-collected language sounds like asking for an immediate system crash. But MicroPython actually allows it as long as you obey one unbreakable rule: zero memory allocation. This episode covers determinism in Python, timers and interrupts. When you need to read a sensor exactly 1,000 times a second, a standard loop with a sleep function will fail. Garbage collection and background tasks introduce random delays, destroying your timing. To get deterministic behavior, you need a hardware timer. Using the machine module, you configure a timer object to fire periodically and execute a specific callback function. This callback is your interrupt service routine, or ISR. Timers trigger either soft or hard interrupts. A soft interrupt is scheduled by the MicroPython virtual machine when it is safe to do so. You write a soft ISR just like normal Python code. It can create objects, append to lists, and handle floating point numbers. The downside is latency. If the garbage collector is actively running when the timer fires, your soft interrupt simply waits in line. If you need strict timing accuracy, you configure the timer to trigger a hard interrupt. A hard interrupt stops the processor immediately. It bypasses the virtual machine and runs your callback instantly. Here is the key insight. Because a hard interrupt preempts the current system state, it might interrupt the memory manager itself. If your ISR tries to allocate memory on the heap while the heap is in the middle of being modified, the microcontroller will crash. This constraint dictates exactly how you write hard ISRs. You cannot allocate any memory. No creating lists, no building dictionaries, no string manipulation. Even floating point math is strictly forbidden, because in Python, every float is a newly allocated object on the heap. Your code must execute fast, rely on integer math, and use pre-existing memory structures. Consider a scenario where a hardware timer fires at 1,000 Hz. Every millisecond, the ISR reads a sensor value. Since you cannot append the reading to a list, you must pre-allocate your storage before starting the timer. You create a byte array of 1,000 bytes in your main program. You also define a global index variable. When the timer fires, the ISR reads the sensor. It updates the global index, stores the raw integer into the byte array at that position, and exits. The memory space was reserved entirely up front. The interrupt just updates it in place, guaranteeing jitter-free execution. Once the buffer is full, the ISR needs to hand the data off to the main program. You cannot trigger a complex data processing function directly from the hard ISR. Instead, you use MicroPython.schedule. This function takes a reference to a callback and queues it to run as soon as the system returns to a safe, soft execution state. Handling hardware interrupts forces you to stop thinking about Python as an infinite resource pool and start tracking exactly when and where your memory is assigned. Check the official MicroPython documentation for the specific interrupt behaviors of your hardware port, and try intentionally breaking the memory rules on your own board to see how the system reacts. If you want to suggest topics for our next series, drop by devstories.eu. I would like to take a moment to thank you for listening. It helps us a lot. Have a great one.